So, good evening, everyone. So, our today's session is starting from 2 p.m. And for the consecutive two sessions, the main speaker will be Dr. Nasimuddin. Dr. Nasimuddin currently is a principal scientist at the Institute of Infocom Research, ESTAR, Singapore, with over 250 published papers, 3 granted patents, and 4 additional patents filed. Dr. Nasimuddin is a prolific contributor to the field. He has also entitled 3 books, including a notable volume on microstrip antennas. He also recognized as the top 2% of the world scientists in 2023-24. He is esteemed for his work as a distinguished speaker, reviewer, and organizer of different sessions and conferences. As a senior member of IEEE and IEEE APS, Dr. Nasimuddin has received several awards, including Ursi Young Scientist Award in 2005, IEEE APS Exceptional Performance Reviewer Awards. He serves as an associate editor for the IEEE Open Journal of Antennas and Propagation and is actively involved with editorial boards of leading journals in antennas and propagation. Additionally, he was the chair of the IEEE Singapore MTT-AP Joint Chapter from 2021 to 2022. So now, Dr. Nasimuddin, the session is over you. So now you can start your session and go forward with your valuable talk. Thank you.
Okay, thank you so much for wonderful introductions, Professor Karmakar, and good afternoon, everyone. So today I will discuss about the advanced antenna configuration for efficient RF energy harvesting. I think this is the last day, so you will be very expert now RF energy harvesting and the RF circuits for RF energy harvesting system and wireless transfer. So outline of my presentation. So I will discuss a little bit the background of the energy harvesting. What is the energy harvesting? Why we need the energy harvesting? And I will discuss some motivation about the energy harvesting. And then I will discuss some background very long back, I think more than 100 years ago, I think they started this idea. And then we'll discuss some current and future application and some design consideration of RF energy harvesting, how we can design the efficient RF energy harvesting system. And I will discuss in detail what kind of the structures for energy harvesting system. And I will discuss about the RF energy harvesting sources and the polarization, what is the effect of the polarization, impact of the polarization of the energy harvesting system. And some of my research on the circular polarized antenna, based rectina, and the whole system based on our student work, I will discuss in details. And last but not least, I will conclude my presentation. So, you know, in our surrounding, our environment have the rich source of the ambient source we can use freely. So we have the sunlight, RF, wind, thermal, and vibration. There are so many ambient sources which we can use. We can use for harvesting the energy from these sources freely available in our environment. So we have to think how we can harvest energy from these sources. So we can harvest energy for low power devices like low power sensors and wireless sensor network, IoTs, moisture sensor, medical implantable devices, and the smartphone. And now we're talking about the smart city or smart building. For smart city, smart building, we have thousands of the sensors. So how we can power up of these sensors? This is also very interesting to use the energy harvesting system. So energy harvesting is nothing. We can capture the freely available sources which can be harvest and convert to the electrical energy for the low power electronics devices. This is the energy harvesting. So where we can use the energy harvesting, why we use? Because some place there the no power line or no power line is inaccessible. So we can use the energy harvesting system. And other challenging is we can replace the battery. And when the power is needed, only when ambient energies are present. So there are so many low power sensor. We can power up the sensor using the energy harvesting system, or we can connect the energy harvesting system with the sensor. So the sensor can be the self-power devices. So I just discussed our environment have the very rich for the ambient energy sources like solar, wind, hydro, thermal, vibration, human body heat, and the RF and EM radiation, because the radiation nowadays increasing drastically. So application I have discussed there, the low power devices, sensor IoTs, biomedical, environmental monitoring, and the agriculture. There are so many sensors in the nowadays agriculture and some portable devices. So one is the important application of the need of the energy harvesting system. We can replace the battery. So energy harvesting system can replace the battery because the most of the sensor of the battery size is very large. So the size is bulky. So the most important part of the energy harvesting we can use for the replace the battery and reducing the maintenance, because you need to change the battery. Battery life is the 2 year, 3 year like this. After that, you have to change. So the important part of the energy harvesting requirement for the replacement of the battery. And other research area is the need for the how we can neutralize the energy, harvested energy equal to the power consumption of the low power sensor. So once we have reached this point, once we equalize the energy, harvested energy matched to the power consumption of the low power devices, then we can use the um, energy harvesting based self power sensors. And the other important is the self power sensor. So the device can be included, the energy harvested device can be included in the IoT sensors, so which can be the self power. So this is also important. And other one nowadays, the IC and other thing, we can have the IC is very small. So how we can connect this energy harvesting system? This is also challenging. And now autonomous and the compact system also require the energy harvesting system, which the device have a very compact size. There's no any charging external charge. No need the external charges as well thing. So there are the different type of the technique of the energy harvesting. Solar energy. So solar energy need the photovoltaic cells and solar thermal energy and vibration and mechanical and thermal energy harvesting. And today my talk on the RF energy harvesting. I will discuss in more details the what kind of the antenna is good and what is the polarization and the thing, and wind energy harvesting and the hydro energy harvesting and human body, and we can also generate the energy from the human. If you are running or you are moving around, so you can create the energy and you can use as a energy harvesting for. And there is some chemical energy harvesting. So this is the one very good figure. You can see the energy harvesting different type RF energy harvester. Harvester use the RF energy our surrounding, and solar needs the photovoltaic cell need the sun bulb or the cloudy environment. There's a thermal capacitor generator, electromagnetic. You can based on the vibration, or you can generate the energy. So there are different type of the energy harvester available you can use. And there's also now talking about the how we can use the hybrid type of the energy harvester, because the RF energy you can get the 24 hours. So other ambient sources the based on the weather condition, or so one energy harvester is 24 hours, the energy harvester. So you can include the like the solar panel with the RF energy harvester, or you have the thermal generator, or you can have the different combination of the hybrid energy harvester design. So this is the just for the repetition of the different. We have the energy sources and the harvester, and then other important part is the how we can store the energy, harvested energy. So we have the battery or superconductor, which we can use the energy for the sensor or the thing. So these are sources, and this is the harvester, and this is the storage. So the energy density wise, the wind energy have the largest density. Like you can get the 177 microwatt per centimeter square, and after that is the solar is the very large energy density, and thermal and the RF ambient RF. So ambient RF have the very small energy density compared to the other energy harvester. So in the future, the RF devices increasing and drastically increasing the baseband and the RF devices which can radiate 24 hours. So this ambient energy harvest, the ambient RF density will increase in future drastically. So there are some power density which are published in some papers. So you can see here the efficiency of the RF energy harvester is higher compared to the other energy harvester system. So if you look at the solar energy outdoor and indoor, only the 10 to 25%, and the vibration piezoelectric, there's the 25 to 50%, and only you can see the RF energy harvesting efficiency is 30 to 80%. So now the technology increasing some and enhancements in the technology, so this can be also enhanced. And there are some experimental data available for RF power harvesting. So based on the distance and the frequency band, and the power can be harvested around to 60 microwatt, and some 80, 180. It depends on the distance from the source. So most of the sensor for biomedical or low power sensor in within this range, 2 micro, 1600 microwatt. So there are some future applications. So in future, there are the home autonomous or smart healthcare systems and smart vehicle tracking. So you need the sensor, and there are smart agriculture monitoring. You need a lot of sensor, moisture sensor, soil moisture sensor, or there are so many sensors. Smart the building. You need the surveillance of the building. So you have so many sensors. So how we can power up this sensor? And other important in the future is the smart infrastructure monitoring. So we have the large city or large building. How you can monitoring the building smartly. So you need a lot of sensor to monitoring the building or city. So in future, I think this area may be very hot because if you need any smart thing or smart city or smart building, so you have to have the sensor. So if you have the sensor, you need the power. Power is very important. So how we can power up the thousand of the sensor in the smart city or smart building? So have to think how we can use the energy harvesting system to power up these sensor, or how we can make the self-power sensor using the energy harvesting. Or now the research also going, we can transfer simultaneously the power and the information. So this area also very, very good for in future. So these are some applications in the future: IoT and wireless sensor networks, wearable electronics, smart city and infrastructure I just discussed, and the wireless charging. There are so many small power consumption devices you can wirelessly charging, and IoT in agriculture. This is also very hot topic nowadays. So agriculture also need the sensors. to monitor the conditions of the soil, weather, and the crop health. Environmental monitoring, RFID, near field communications, wireless communication. So wireless communication I have discussed just now. So in wireless communication, we can charge the communication device and then by using the energy harvester, and we can transfer the information also simultaneously. And building automation and now the military and defense also, we can use the energy harvesting system. So in future, there are some future technology of the wireless power transfer. You can charge the mobile. I think these are available in the market. Toothbrush charging my mobile, and vehicles also like car. You can charge using the wireless power transfer technology. In future, I think there are some smart building how you can charge your vehicles. Just to in the car park, you have the wireless power transfer smart grid. You can charge your vehicles. And there are some country, I think Japan have some road. You can the bus or any electric car or bus can charge on the road, like charging road or like this electric charging road like that, the one lane like that. So the vehicles can charge automatically. No need any petrol or other thing power. So this is also in future all everything going to smart. So this area is very hot area. Another thing, we can use the solar power satellite. The satellite can send the power to the ground, the microwave receiving antenna here, and the antenna can convert to the power in the electricity. So this is also very hot because in space you have the solar very high solar power, so you can send to the ground. And other is the wireless charge vehicles on the way. This is also, if you have the red light or other thing, you can charge your vehicles. And in future, some electric train also wirelessly can develop the wireless power train, electric train. And there are some smart house, how we can charge the devices in the smart house. There are in house, there are some sensors, so you can wirelessly charge these sensors without any connection wire. And there are some in the tsunami time, any disaster emergency, you can have the power source like you have the drone, or you have the and using the drone you can send the power for start the communication, because in the emergency some communication line is disturbed, so wirelessly you can charge the communication station, or you can have some communication system. And then we have the in hospital, so the patient have some tag or some sensor. The sensor can send the information to the doctor, and doctor can see on his screen the patient in the room or out. So this also can be used for the smart medical patient rooms and that. And there's some power, how we can develop the clean power station. So we have the renewable energy power stations, the sun, wind, and the hydro or thermal, and combining this and to send to the power transmitting antenna, can send to the other antenna like that. We can send to the buildings and factories and everything. So using the wirelessly or and the firefighting drones getting its power wirelessly from the firefighting vehicles. So if you have the transmitter on the firefighting bus, so you can transmit the power to the drone, which can carry the water pipe for fire. So this is also, I think, in future there's some idea how we can use the wirelessly power transfer or RF energy harvesting based system to power up some very useful applications. So there are some body area, wireless body area network sensor. So you have the sensors, so many sensors. So you can use the energy harvester to power up these sensors, because if you are running, so you can generate the energy. So using that energy, you can power up these sensors to detect the heart rate also. So there are so many sensors in the hospital also, and these are all connecting with the this internet, so you can check the data. The thing. So this is also very good area for and the future for bio wireless body area networks. And these are the some because the biomedical application requires the low power energy, very low power, like 10 microwatt or 1 milliwatt, like this. So these power for these medical implantable devices, we can power up using the energy harvesting. So there are some calculation in this paper, very interesting paper. So how much power required for these sensor bone growth simulator or cardiac pacemaker, drug pump. So this is the microwatt, only microwatt, like 5 to 20 and 100 watt. So based on this energy harvesting, you can power up the pacemaker or cardiac pacemaker without, because the battery is not good for human body. So now the research, the doctor thinking how we can power up this pacemaker to using without battery. So this is also, I think, very breakthrough if this work. And other is just I discuss the agriculture farming, how we can agriculture is smart, how we can make the agriculture smarter. So using the IoT uh, self self power IoT sensing system, we can make the agriculture also very smart in the future. So now I come to the my talk. So the main motivation of the RF energy harvesting or wireless power transfer, how we can powering the electronic device using the RF electronic wave wirelessly. This is the main motivation. So cutting the cables and battery, the future of the wireless power sources. So why we need the RF energy harvesting? So no power wire. One is the important. So no need any wire. So we can transfer the power without any wire. No power available or not reachable places. So other important things, we can replace the battery. Battery is not good, and this is also not for good for environment. Sometimes is the very dangerous for explosion or something like, and need the recharge or replace. So the wireless power transfer and the energy harvesting, not big difference. Only the difference is the source. So wireless power transfer system based on the dedicated source. So power delivered wirelessly to the electronic device from the dedicated source, no wire. And the RF energy harvesting, you should have, it depend on the environment, ambient sources. So if the environment is the very high density of the RF, we can use the RF energy harvesting. If the power density is very low, you cannot use, because you should have the minimum power to turn on your diode. If the power level is very small, so you cannot use this energy harvester. So I will discuss little bit how this concept developed. So in 1800, I think there's some early theoretical foundation of this wireless power transfer or the RF energy harvesting. So there the one Australian scientist discovered that the electric current create a magnetic field around it. Then Ampere expand on his finding, and he quantified the magnetic field generated by the electric currents. Then Biot-Savart law calculates the magnetic field produced by the electric current. Faraday law, and then we have the Maxwell equations. I think Maxwell equation is the theoretical work, basic theoretical work of this wireless power transfer. The first theoretical basis of the wireless power transfer is the Maxwell equation. The Maxwell equation proved experimentally by the Hertz and the transmission of the wireless signal by the Marconi. So these are the theoretical foundations and then some proof by the Hertz and Marconi. And the first wireless power transfer system developed by the Tesla is, I think, more than 100 years ago in the, around 1980, 19, 1890, 1889. So after that, the Professor V.C. Brown invented the rectina, which can be change the power in the for electric device. So he patented the first patent on the rectina in I think 1960 around there. So after that, I think he has some experiment to power up the small aeroplane around very small distance to check his experiment. And there the some concept of the space-based solar power by the glass. After that, I think the commercial development started in 1980. So there the EPI or the some power cost have the some product in the market. And there's so many, I think now market, there the some company I have listed here. Now the commercially development started. And this is the now very hot topic for some, because the IoT sensor or this the wireless sensor network, they need the power, how the power of this sensor. So the research is going on this area. And there are so many companies now, startup company working on in this area. But still, I think a lot of challenge because the ambient RF source is still very low power density. And the other problem is the diode. Diode is still, if you have the very high power, still cannot convert the all power because there's a down voltage or the problem. So this is the just comparison between the wireless power transfer and the RF energy harvesting. As I discussed, the wireless power transfer need the dedicated source, and the RF energy harvesting based on the ambient source. So designing antenna or matching circuit for wireless power transfer very easy because you know the frequency, antenna gain, and power available for the receiver at the receiver. So you can design antenna power or the matching circuit very easily. But for RF energy harvesting, you don't know anything. So we have to first to survey this power density, what kind of the band available, what is the power density, and there are so many things you need to survey. And the wireless power transfer not free, but the RF energy harvester can be free if you're using the ambient source. And the energy we cannot control in the RF energy harvesting because this is not controllable. And the wireless power transfer, because this is the dedicated source, we can control. Energy cannot control, right? Then this one only designing very challenging for the matching circuit for RF energy harvesting very challenging because the always changing the power level, daytime different, the nighttime different, slightly different, or some the band change or frequency change, polarization change. So the matching is effective because we are using the diode. So between the antenna and diode have the some non-linearity. So the antenna part is capture the RF waves from the environment, and the rectifier circuit convert the received power, RF power, into DC. And while the matching circuit should ensure the maximum power can transfer to the rectifier. Otherwise, you can lose the power. But in theoretical, practical the system should operate without any external power. So if the energy harvester system need power, so no meaning of the energy harvesting, ambient energy harvesting. Okay, so this is the just very typical diagram of the energy harvesting. So we have the dedicated RF source, ambient RF source, unknown sources. So in environment, we have the different type of the sources. So the antenna should capture most of the energy surrounding the antenna or surrounding the environment where we place the sensor. And then we have the matching circuit. So matching circuit should transfer the all power to the rectifier. If matching is not good between the antenna and rectifier, so you cannot transfer the capture power. You have the very good antenna, you can capture all energy, but if you not transfer the all energy to the rectifier, you will lose the efficiency of the this rectina. So rectina is the main part. Rectina is the heart of the RF energy harvesting system. Then we have the power measurement, management, the storage and control unit. Then we have the load, low power devices, and there are some transmitter, transmitter or the MCU need to consider. But for the RF energy harvesting system, and the rectina is the main concern. So the antenna and rectifier and with matching. If matching between the rectifier and antenna is good, then you can design the very efficient and RF energy harvesting system. And this is the very, very challenging because the antenna is the passive and we have the rectifier is the active. So this matching load change based on the load, based on the power density and lot of things. So the matching, how we can design the tunable type matching, which always the antenna match with rectifier. This is also very challenging. So the number of the base station wireless devices and the RF system, radiation sources continuously increasing drastically worldwide. So the power density increasing in the environment drastically. And this power, only the for small portion of the power is used for the communication. The rest is the lost in the heat dissipation absorbed by the material. So this the rest power we can use for the clean source using the energy harvesting system. So in future, this power is the density increasing. So a lot of power we can use for the energy harvesting. This is the main concept of the RF energy harvesting. So harvested power from the ambient sources can serve as an energy supply for the various low power devices. So you can see this graph, the innovation in the technology increasing. So the power consumption of the sensor or the electronic devices decreasing with time because the innovation in the technology, semiconductor innovations increasing. And the harvested power increasing due to the increasing the base station or wireless devices or satellite are now increasing also satellite, radars. There are so many wireless devices increasing drastically. So this power also increasing. So in future, I think this graph is crossed over, and then we can use the energy harvested based ambient energy harvested based sensors, IoTs in the future for sensing or communication also. So this is also the same diagram, but this one I will discuss about the interface. So we have here the electromagnetic wave antenna, receiving antenna, and here we have the rectifier, energy storage, power management, and load and low power. So for designing the RF energy harvesting, the researchers should know the both field, EM field or antenna and electronic circuit, power management or this storage. Then you can design very efficient RF energy harvesting system. So if you know the only antenna, so antenna can you can design very good antenna which can receive the most of the energy surrounding. But if you not designing very good impedance matching between the rectifier and antenna, you will lose energy here. So you will the received power you cannot transfer to the rectifier. So no point. So have to have everything very efficient way. You have to have perfect matching circuit designer because you have the wide power density based this matching circuit and different band. If you have the multi-band or wide band, you have to think how the matching circuit is good for wide band or different load. If you change the load also, the matching is changed because uh, this is the active devices you are using here. So the best designer can be if you have the good team with combination of the antenna, RF or EM field, and the other group is the circuit, power management, or this the low power devices information. Then you can design very efficient RF energy harvesting system. So this is the just a very simple calculation with the line of proper line of sight the structure. You have the transmitting antenna, you have receiving antenna, distance between the transmitting and the receiving antenna D. So you have to calculate the what is the power available for the receiver and what kind of the power you have. So if you change the distance, this power available at the for receiver is the drastically change with distance. So if you change the like you have the very far from the like base stations or TV station or TV tower, so the power is very small. So if you are nearby in the base station or TV tower, you can use this ambient RF energy based this sensor. So this is just calculation of the GSM band 900. If you have the 39 dB watt and your transmitting antenna gain is the 15 dB and your receiving, it means your harvester gain is the only 5 dB. So if you have the 1 kilometer far away, so you have very small power, only minus 35. Because the path loss, free space path loss is increasing with the distance. So you have to calculate this information for designing the RF energy harvester. You should know the where the or you have to do the some survey what kind of the energy available of the for the harvester. So this is the just a very conceptual block diagram of the energy harvesting system design. So the first you have to select the sensor. This sensor you want to use as the RF energy harvester based power. So you know the power requirement. Then you have to do the survey or you have to do the some measurement. What kind of the RF source is available nearby the this your where you want to place the energy harvester based sensor. So you have to check the power density, what kind of the power density available, and what kind of the RF sources, operating frequency band, and what is the distance from your source from your devices, and the available power for the harvesting. So you have the multi-band or wide band and this available RF sources. So based on that, you can design the antenna, multi-band antenna or wide band antenna, rectifier, voltage multiplier. So then you have to design the receiving antenna based on the available frequency band. So you can design this thing very easily, but you should measure this power density in the daytime 2-3 times in the 24 hours. So you have the average of the power. average information of the power available for the harvesting. So the impedance matching is also again very challenging, and the rectifier circuit and the voltage multiplier. You can use the multi-stage rectifier if the power is low. This is the harvester designer. This is the very challenging. And then you have to check the harvested power, how much the power you can harvest from this design. If the harvested power is equal to the power consumption by the sensor, then I think you can go and connect the harvester to the sensor. If not, then you have to think how can increase the harvested power. So you have the different way. So you can use the multiple receiver or multiple rectifier to power up. And there's some booster of the DC to DC booster you can use. This is the same things, just in the some outlines, some useful design guideline considerations for efficient alpha energy harvesting. So first you have to do the survey. First you have to know the power consumption. Then you have to do the survey, measure the RF ambient sources, RF sources survey. So if you have the multi-band like this survey have the 3-band, 900 or this 1 point something, 1.8 and 2.45 or something. So based on that, you can design the tri-band antenna, and you can get the energy from the 3-band, and you can connect with the sensor. So they have some paper have, I think, demonstrated this kind of research in the paper. Another is the indoor. So they use the Wi-Fi 2.4 to this is 2.4 to 2.48. And they have done in the survey in the one office, the small office, and they have designed the harvester 2x2 array because the power is not so high. So to power up this sensor, they need the power, more power. So they have designed 2x2 unit to power up the sensor. So this is the first to estimate the power consumption, then survey what kind of power density surrounding the proposed energy harvester based sensor. And then you have to design the efficient wideband or multi-band antenna, or the antenna should be wide beam. So if you have the wide beam antenna, you can receive the energy from all directions. And then you have to design the efficient rectifier, because there's a different topology of the rectifier. You can use the efficient topology to achieve the high rectification efficiency. Design matching circuit also very important. And there if you have the multiple sources, you can design the multiple. If the power is low, so you can have the multiple receiver, and then you can use the either DC combining or RF combining based on the power. So if power is very low, so you can go the RF combining. You can combine the RF. If RF power is okay, then you can have the DC combining. So you have the multiple harvester. You can just combine the DC. You can have the more energy for the sensors. So there are some example in the literature or in the some commercially available also. So like base station need the temperature reading. So nearby the base station is very easy to design. So they just connected the temperature sensor based on the energy harvesting. So you can get the information without going to climb up on the base station. So only the distance is 1.4 meters. So you have the enough energy to harvest for this sensor. So like this application, I think the RF energy harvesting now okay, but in future maybe the density increasing, so you can use the energy harvesting based this sensor. There are so many, I think, literature nowadays, a lot of literature based on this type of the research. So now I will discuss the antenna configuration for RF energy harvesting. So configuration, antenna have the different configuration. So it depend on the how you are using the which type of the sensor and what is the space constant of the for sensor. So and there are some configurations depend on the requirement, and the polarization also very important for the energy harvesting. So you have to consider the antenna which can receive the most of the polarized wave, and bandwidth. If you have the wide bandwidth spectrum available your surrounding, so you have to design, you have to consider the wider bandwidth antenna. Radiation pattern also very important. So if you have the wide beam radiation pattern, you can receive the more energy. And direction again also very important, but the most of the sensor very small, so the antenna gain is also how we can design the high gain antenna for small space. This is also very challenging. Beam width and coverage also important. So there are the different type of the antenna. The planar antenna, wideband antenna, high gain directional antenna, conformal antenna, wide beam antenna, dual multi-band antenna, monopole like this, circular, dual polarized. Dual polarized antenna and circular polarized antenna are very good for best, I think, for the energy harvesting, if the space is no issue. Nowadays, the transparent antenna, mesh-based antenna is also very important for future, because the most of the building now using the glass. So in future can be used the transparent antenna on the building glass, or you can put the anywhere this transparent antenna. And the meta material based, now the research going on the reconfigurable intelligent surface, how we can make the reconfigurable antenna intelligent surface which can be transfer the power and also send the receive and transmit the information also. And there's a beam steering, beam switching antenna also can be used for the wireless power transfer to different direction, or receive the energy from different direction for energy harvest. There's a great type of array antenna, very low cost. You can have the multi-beam antenna, which can receive the energy from multi-direction. Reconfigurable antenna, and there the dielectric resonator antenna also can be used for the energy harvester. Maybe some of the I think talk maybe they discover that these some dielectric resonator antenna or reconfigurable antenna. So the wideband high gain antenna configuration with wide coverage, which can receive the energy from the all direction, is good choice for RF energy harvesting. So in the real ambient RF energy sources, we don't know what kind of the polarized wave available in our surrounding, what kind of the wave, what is the frequency, and there are so many source, and wave is hitting some building or other thing metal, so polarization also change. Like circular polarized hit with some metal, so the right hand to change to left hand. So the polarization mismatch also. So how we can design the antenna which can receive the most of the available EM wave or EM energy surrounding the harvester. So this is also very challenging. So we have the different type of the waves in our surrounding. So circular polarized antenna have some advantage. So the circular polarized antenna is the polarization independent. So wave in any direction can receive any tilted or any angle. Another important is the multipath mitigation. So the circular polarized antenna handle the reflection and the multipath interference better, reducing the signal fading and reduce the interference and design flexibility. And the other important part of the circular polarized antenna, no need to align the polarization. So any orientation, the circular polarized antenna can receive the same wave, or most of the all wave in the surrounding. Can we have the break for 5 minutes or 10 minutes later on? So the other part is the antenna configuration and the antenna radiation patterns. So the radiation patterns, I think, very important, like the beam patterns. If you have the wider beam antenna, wide beam antenna, which can receive the energy from all directions, is very good for the energy harvesting. And if you know the polarization, or if you want to use the like wireless power transfer, so you can use the very high gain antenna. You can transfer the power, because you know the antenna, transmitting antenna, you can align the polarization with high gain antenna. For energy harvester, so you should have the wide beam with high gain antenna. So directional antenna generally for the wireless power transfer. So if you want to the high gain, so you have to have the sectorized antenna. So you can put the high gain antenna in the different sector, which can receive the energy from all directions. There the multi-beam antenna, which can receive the energy from multiple directions. But the multi-beam antenna needs some switching, which require the power. So this is not a good choice for the real RF energy harvester. And there are some satellite antenna also, which can receive the energy from all directions, and then you can combine like either RF combining or DC combining, if you have the based on the power available. So I will discuss now the polarization, antenna polarization. The polarization of the electromagnetic wave is defined by the shape and the orientation of the E vector. So the antenna polarization, we can define the far field in either the vertical or horizontal or circular, or both have the dual polarized, like circular and or the vertical and horizontal. So generally there are the two types, linear polarized and circular polarized. Linear polarized have the vertical and horizontal, and the circular polarized have the right and left. So the one factor between the linear and circular polarized is the axial ratio. For circular polarization, this is the extra parameter which define the quality of the circular polarized antenna. So this axial ratio we define like major axis and minor axis. If the major and minor axis is same, so we have the ratio 1 or 0 dB. This one is the perfect circular polarized. It means the both minor and major axis same. So we have the perfect circular polarization. But in practically, we are defining this the ratio. If you have the ratio 2 or 3 dB or half 0.5, so we call the 3 dB. So the circular polarized antenna bandwidth defined by based on the axial ratio value. So this is the vertical polarized, this is the horizontal polarized, is the dual polarized. We have the both vertical and horizontal. And this is the circular polarized. So we have the combination of the horizontal polarized and vertical polarized. For circular polarization, there is the condition you should have the two mode, vertical and horizontal, with 90-degree phase difference. So you can generate the circular polarized. Otherwise, you cannot. If you know not a 90-degree phase difference, so you have the like the dual polarized. So circular polarized condition, you should have the two mode with 90-degree phase difference. 90-degree phase difference, you can generate the circular polarization. So that this just the difference between the circular polarized antenna and the linear polarized antenna. So signal reception, I think the one is the known is the alignment of the transmitter polarization for circular polarized antenna. So the circular polarized antenna can be received any and the transmit in any polarized. But for linear polarized, you should align the transmitting antenna polarization if you are receiving the linear polarized antenna. This is the very, very important big difference between the linear polarized antenna and circular polarized antenna. And other big difference is the Faraday effects sensitivity. So if the wave linear polarized wave transmit from this Faraday effect or any magnetic or there are some ionosphere layer, so the polarization change. But the circular polarized signal is less effective with this Faraday sensitivity. The ionospheric effect is very less for circular polarized antenna. And the other thing application, the main, I think this one, without the orientation independent. So you can put the circular polarized antenna in any orientation. No need to align with the transmitting antenna. So this is also very important slide to think how we can use the antenna which can receive the most of the energy. So you can see that this is the dual polarized antenna and this is the circular polarized antenna. And these two antenna can receive the most of the wave with the half of the efficiency, coupling efficiency. But other antenna, like if you put the horizontal polarized antenna in the RF energy harvesting, so you cannot receive the vertical polarized wave like this. So antenna selection is also very important, polarization selection. So for the real application of this energy harvesting, you should use either dual polarized antenna or the circular polarized antenna, which can be received any polarized waves, our surrounding. So polarization of the antenna is also very, very important for communication or this energy harvesting, and also for the wireless power transfer. So you have to align for wireless power transfer, you have to align the transmitter antenna polarization to the receiving antenna polarization. Then you can transfer the efficient power. So there are the various configurations of the antenna. Can we have the break for the 10 minutes? Hello, Karmakar? Hello, can you hear me?
Yes, sir. Yeah.
Can we have the break around 5 to 10 minutes?
Sir, actually, just a minute. You are not audible. Just give me some moment. Just a minute, sir. Some issues there with my system.
Oh.
Just a minute, sir. Just a minute. Give me some moment. Yeah, sir, please tell me.
Okay, wait. Can we have the 5 to 10 minute break?
So actually, okay, sir, you can take it. Actually, your session, your first session is up to 3:30. So if you tell that we can start the next session from 3:30.
Around only 5 minutes, 10 minutes is okay, I think, for me.
After, sir, actually, the thing is that you have two sessions.
Okay,
sir,
yeah.
You have two sessions. The first session should continue up to 3:30.
Up to 3:30.
3:30. You can check the schedule and.
Okay. We can use. Okay.
So I think that you can continue up to more 15 minutes. After that, we can again restart from 3:30.
Okay, got it. Okay. So this one, there are the various. Can you hear me now?
Yeah. You're audible.
Okay. The various antenna configuration. So if you want to very small antenna, sensor, want to fix this antenna to the sensor, so you have to design very small antenna, very compact antenna. So we have designed, this is for the 900 and for some temperature sensor. So we design very small antenna. So there are the different configurations. You can see that this is just monopole, Z-shaped monopole, circular polarization antenna. This is the high gain wideband circular polarized antenna. You can have the very high gain, this around the 8 to 10 dB thin antenna. And we have also designed some meta surface, meta material based circular polarized antenna for energy harvesting, which can enhance the efficiency of the harvester. And this antenna is very interesting. I think somebody published in the UK, and they used designed the 6-band dual circular polarized antenna, which can receive the energy from the 6-band with dual circular polarized. This is very interesting antenna. So there are some grid type antenna. So grid antenna have the quality, can have the beam in the different direction based on the excitation. So beam can be go in the different direction. So these are some grid array antenna. So this type of antenna can be used for the hybrid type of the energy harvester design. You can put the solar panel behind of this, and you can use this grid for the RF energy harvesting. This is the dual polarized, and this is the dual circular polarized antenna. You can have the dual polarized with the dual feed. So this is also dual polarized. So you need for dual polarized antenna, you need the 2 feet. So you have to connect the rectifier with the 2 rectifier and then combine the DC combining, or you combine the RF combine and put the 1 DC combining. And this is also very interesting design, which have the quasi-isotropic antenna pattern. You can receive the energy from all directions. This is the meta surface based antenna. This is meta surface based antenna. Meta surface is also very interesting for RF energy harvester because the meta surface unit is very small, around lambda by 10. So you have the more unit in the limited space, so you can get the more energy. This is the sector type antenna. You can get the energy from all directions and then you can combine. Because this is the high gain and beam, you can receive the more energy from all directions and combine. This is a multi-beam antenna for grid type antenna. And one of the professor from the US, Ramasamy, proposed some like a power bank. You have the multiple antenna connected with the multi-band antenna, and then you can combine like RF combining or DC combining. You can use as a power bank of this type of the structure. And there are the different type of structure available in the literature. So dielectric resonator antenna, I hope somebody will present this area in this series. And there are some dual band inverted F-type antenna, and this is some slotted type antenna can generate the dual band. So in this the comparison, you can see the dielectric resonator antenna has the wider bandwidth and with the higher efficiency. And there are some meta surface based RF energy harvester. This is just a very simple comparison. You can see the patch based antenna. This is the red color, and this is the meta surface based. You can see the meta surface based has the higher efficiency with wideband compared to the patch based array antenna. This is the patch based, and this is the meta surface based. Another comparison you can see here. If you have the patch based efficiency is very low, around 50% or 60%. And if you have this meta surface based, efficiency is very close to 80 and very wide band. So the meta surface enhance the efficiency of the harvester in the same volume of the aperture, the patch aperture based array, or this unit cell based meta surface. You know, the unit cell, the size is very small. I think around lambda by 10 unit cell. So you can put the more unit in the same space like the patch antenna array. So in patch antenna array, the interspacing distance should be lambda by 2. If you have the very less lambda by less than lambda by 2, the gain is dropped drastically. So that's why this area, the interspacing element distance should be lambda by 2. So that's why you cannot put the more element in the patch type of the array. So in the metasurface unit based, the unit cell size is very, very small, lambda by 10. And you can put these metasurface unit very close, no any boundary. So you can put the more harvester and then you can combine. So this is the advantage of the metasurface in for energy harvesting systems. And there are the different type of the metasurface unit. You can connect the 2 diode or 3 diode or, based on the design of the unit cell. So if you want to use the wideband rectifying metasurface, you have the special design. They use the some air gap to enhance the efficiency or enhance the bandwidth and gain also. So you can design very, very high efficiency metasurface based RF energy harvester. You can see here, close to the 90% or 95%. Here you can see. And the other important thing is the angle. If the wave coming from the different angle, still the efficiency is very good. In the different angle, you can see here. This is the major efficiency close to the more than 50, 60. So this is very good for generally the patch based efficiency around 30%, 30%, 20, 30%. And another one is the high efficiency ambient RF energy harvesting by using a material perfect absorber. So they have designed using the SRR based harvester unit cell and using the metasurface based unit cell, and they have designed very efficient. You can see this efficiency is I think very 80%. This is the major efficiency RF to DC harvesting efficiency around 80%. This is a very good for the harvester 80% efficiency. So one of the PhD students from Australia think how we can design the smart house based on the energy harvesting system. So that time they use the array of the rectinas, patch-based array of the rectina. You can put the array of the rectina on the roof of the house, or you can have the wall. So you have a lot of space in the house. You can put everywhere. So now discover the transparent antenna based retina. You can put even the window, everywhere you can put. The idea here, you have the harvester or retina. You can just a DC combining from all the harvester. You can get a lot of energy because the space in the house, the roof and the wall have the more space. It means you can receive the more energy because in RF or in the antenna, if you have the larger aperture, you can receive the more energy. So this is a very good idea. If you if you have the ambient source surrounding your area, you can design the smart small house, and this house can be used without electricity. You can charge your mobile or camera, or you have the sensor. You can charge up your sensor. So this is very good idea. In maybe future, this idea can be have the practical way to design, because now the metasurface, we have the metasurface. We can put the metasurface over the roof, or even we can put the transparent metasurface on the glass window, or everywhere we can put. I think no, because now technology very advanced. So can use even the material also can be used as the harvester. There's you have the hybrid type of the energy harvester like solar and RF. You can combine. You can put in your roof on the. And this is one of our students designed the matter surface with some beam forming. We can change the beam in the different direction based on the pattern generated. And this pattern can be electronically changed. But this is the passive. We use the passive to just verify the idea. So if you have the diode based or the switch based this pattern, you can switch this unit cell, you can change the beam, or you can use this kind of the patterns in the patient house, in medical or hospitals, uh, and then you can use as the tracking the patient or charge up their sensor, and you can get the simultaneously you can transfer the information and the charge of the sensor of the battery of the patient. Or so this is just a very low level work, not very just it was just the idea. And there's the one very interesting paper in some university. They have done first the in university survey around 0.3 kilometer from cellular tower and 6.2 kilometer from the TV tower. So you can see that there the multi-band signal available around the university campus. So we have the multiple sources. So based on this survey, they have designed the 5-band or 6-band antenna, which can receive the energy from available energy surrounding the university campus. So they have used the two topologies. One is the RF combining. So the multi-band antenna, they designed this antenna, multi-band antenna. They have used the RF combining, and the single band antenna, this antenna for FM signal, receiving the FM signal because the frequency is very low. So they use the helix type of antenna to reduce the size. Then they have the RF combining first, and then they change to the DC using a rectifier, and then both they can have the DC combining. So overall, I think they can get the large power, combining power. So if you have the multiple unit like this, you can combine DC combining, so you have the more power. So if you have the space in university or anywhere, you can put like this harvester and combine like DC combining. You can charge up to some sensors or some low power lights or something. So this is very good idea how we can use the different topology like RF combining, DC combining with different type of the antenna. And this is very good, interesting work. So this I have discussed. There are some transparent material-based antenna. You can put some your transparent wall or your car or your vehicles. You can put the antenna, or you can use the transparent antenna for your hybrid type of the harvester designing. So this transparent